Today we are going to discuss maximum power transfer theorem. We know theorems are meant for helping us in solving networks.
Let's move on to the theorem.
The maximum power transfer theorem states that in any electric circuit, maximum power occurs across the load resistance when the value of the load resistor is equal to the resistance of the network, looking back from the load terminals, all the sources being replaced by its internal resistance. From the name itself, it is clear that this theorem deals with the maximum power. In order to obtain maximum power across the load terminal, we need to decide the value of the load resistance. How can we decide the value of load resistance? For that, we need to open circuit the load terminal and the effective resistance at that point should be calculated. One thing should be assured that there are no sources in the network. That is, if there is a presence of a voltage source, it should be replaced by a short circuit. And if there is a current source, it should be replaced by an open circuit. This resistance is also called Thevenin's resistance because it is also calculated in the similar manner. Let's have a detailed look of this theorem by solving a circuit.
Let's try to solve this question using maximum power transfer theorem. The circuit is very simple, having only a few components: a 50 volt source, 25 ohm resistor connected in series, and it is having a load resistor. A load resistor terminal is simply the output terminal from which we can collect the output. Our requirement is to find the value of RL in order to get maximum power. So, based on the theorem, we need to redraw the circuit. First, we have to open circuit the load terminal. Then, one more thing should be done. The circuit should be free of any type of sources. That is, this 50 volt should be replaced, and as it is a voltage source, it should be replaced with a short circuit. Step number 1, RL should be drawn as open circuit. Step number 2, 50 volt as short circuit. And this will be a remaining circuit. The value of resistor RL should be calculated as the effective resistance of this remaining circuit, and here there is only a single resistor, so we do not have to find the effective resistance. We can simply write it as 25 ohm. This value can now be substituted to our source network. Put RL is equal to 25 ohm. So by this circuit, we can get maximum power across the load terminal. Now, if we are asked to get the maximum power, then we'll go for the equation of power. We'll write the expression for power as V into I. We have to find the power at this point. For the equation V into I, both the terms V and I over that resistor is unknown. This 50 volt alone is seen as a supply voltage. The current emerges from this voltage source and it flows through these series resistors. If we can find the value of current flowing through this resistor, we can use another expression instead of V into I. Power is equal to I square R. In this case, R can be written as RL. Using Ohm's law, we can write current as V by R. In this case, V is equal to 50 volt. And for the position of R, we are having two resistors in series. So we have to take the effective resistance. We can write it as 25 plus 25. We will get the answer as 1 ampere. The total current that we got now is the same current that passes through load resistor RL. Now we got the value for I, and we have to substitute this value in the power equation. P is equal to I square RL. In the position of I square, we can write it as 1 square, and the RL is the load resistor, and we will write it as 25 ohm. We'll get the final answer as 25 watts. This will be the maximum power that can be attained using this circuit. To have a detailed idea of this theorem, we'll try to solve another question. This question is having two parts. First one, find the value of R to have maximum power transfer in the circuit. And the second part, obtain the amount of maximum power. We can solve this one by one. First, we are going to obtain the value of R. In order to get the value of R, we have to open circuit the load terminal, and if there is any presence of a voltage source or a current source, it should be replaced by its internal resistance. Here we are having a current source, so it should be replaced with an open circuit, and we have two voltage sources over here, so this should be replaced by open circuits. I repeat, load resistor should be open circuited, the current source have to be open circuited, and the voltage source should be short circuited. After completing these steps, we'll be getting a simplified circuit with only 3 resistors in it. The 2 ampere current source is open circuited, the 6 volt and 10 volt voltage sources are short circuited, and the resistor terminal is open circuited. With this simplified circuit, we are going to find the value of R. We have to find the value of R in this position. If we need to get the effective resistance at this point, we'll have to start from the opposite direction. That is, we'll start from the 10 ohm resistor. Starting from here, we'll solve each resistors one by one. We'll check what kind of a connection is between 10 ohm and 5 ohm. One side of 10 ohm is connected to one terminal of 5 ohm, but the other end of 10 ohm is not connected to 5 ohm directly. So it will be a series connection. We know that the effective resistance of a series combination can simply be written as R effective is equal to R1 plus R2, that is 10 plus 5. Now we'll check how this combination is connected to the next resistor, 2 ohm. To have a clear picture, I have redrawn this. The 15 ohm and 2 ohm are connected, and now we have to check what kind of a connection is this. One side of 15 ohm and the other side of 2 ohm are connected here. Similarly, the other sides are also connected. It's having an interconnection in both the sides, so it will be a parallel connection. You know how to calculate the R effective value of a parallel combination. 1 by R effective is equal to 1 by R1 plus 1 by R2. It can also be written as R effective is equal to R1 R2 divided by R1 plus R2. We can substitute the values. 15 into 2 divided by 15 plus 2. And we'll be getting the answer as 1.765 ohm. With this step, we have come up with the answer of the first part, that is, the value of R to get maximum power. We can complete the circuit by substituting the value of R as 1.765 ohm. And in this terminal, we can obtain maximum power. Now the first part of the question is complete. Let's move on to the second part. Obtain the amount of maximum power. We have got the load resistor value. Now we are going to find the amount of power that can be obtained from this load resistor. The expressions for finding out power are P is equal to V into I, or we can write it as V square by R, or we can write I square into R. The choice is ours to pick the relation of our convenience. We are going forward with the relation I square R. In order to get the amount of power, let's try to obtain the value of current that is flowing through the load resistor. This network seems to be like a complex one. While solving such networks, we have to do one thing. We need to apply some theorems or analysis methods that we are familiar with. I have chosen to make use of the Thevenin's method. The reason behind choosing this method is we have already got the value of RTH. As said earlier, RL and RTH are calculated in similar manner. So we can write the value of RL in the position of RTH. One fact that should be highlighted here is for circuit satisfying maximum power transfer condition, the RL and RTH value are same. So we can complete the Thevenin's equivalent circuit with two RTH values. And for this circuit, the only remaining value that should be found out is VOC. And thereby we can obtain maximum power from this load terminal. So the next step is to find VOC. The term VOC in Thevenin's method indicates it is a open circuited voltage. That means we need to open circuit the load terminal and the voltage at that position should be calculated. The network seems to be a little complicated. We'll go for some easy steps. When closely examining the circuit, we can see a current source in parallel with the resistor. A current source in parallel with the resistor combination can be replaced with a voltage source in series with the resistor. The value of the resistor remains same, and to find the value of voltage source, we can utilize Ohm's law. By Ohm's law, V is equal to I into R. So we can write the value of this voltage source as 2 ampere into 10 ohm, that is equal to 20 volt. Let's try to redraw the circuit with this 20 volt voltage source. By inserting this section, our network has become simple. We can now try to get the value of VOC. VOC is seen here. By Kirchhoff's voltage law, we can say that the algebraic sum of voltages in a loop will be equal to 0. So, VOC can be considered as the sum of voltages of 10 volt and the voltage across 2 ohm. Here I am naming the voltage across 2 ohm as V1. V1 can be obtained by getting the value of current in the first loop. So in order to get that, we'll try to separate this first loop alone and get a relation for V1. We know V is equal to I into R. Here current should be found out and the value of R is 2 ohm. So we can represent V1 as 2 into I. The circuit consists of more than one voltage source. So it is not easy to find the value of current. In order to get the value of current, we are applying Kirchhoff's voltage law here also. We can do the KVL calculation in different methods. I have chosen sign convention method. So with sign convention method, I am starting from the first resistor 10 ohm. The potential across the first resistor is represented by the expression V is equal to I into R, and to indicate the potential drop I am using a negative sign. So it can be written as minus 10 into the current I. Now moving on to the next resistor 5 ohm. Here also we are giving a negative sign to indicate the potential drop. So it can be written as minus 5 into I, and the next one is a voltage source. This showing a polarity from positive to negative. In order to represent the polarity of this source, we are representing it as minus 6 volt. The next resistor is 2 ohm and the potential is denoted as minus 2 into I. Now we'll complete the loop. Here we are having a 20 volt supply, and considering the current flow, we can say like it is going from negative to positive. So we are giving it a positive sign and will be writing it as plus 20. So we can complete the KVL equation. Minus 10i minus 5i minus 6 minus 2i plus 20 is equal to 0. By simplifying, we can write it as minus 17i is equal to minus 14, and from that we have obtained the current value 14 by 17 ampere. And from this current value, we can obtain the voltage across 2 ohm resistor. It is written as 2 into I. Now we will try to analyze the second loop. When KVL is applied to this loop, we can get an expression as VOC is equal to 2I plus 10. We can substitute the value of I in this equation. 2 into 14 by 17 plus 10. And we'll obtain it as 11.647 volt. We got the value of VOC and now we are close to our final answer. We can complete the Thevenin's equivalent circuit. We have got the values for all the components VOC, RTH and RL. We need to obtain the maximum power across this load resistor RL, or here in this case it is RTH. So by substituting all the values, our circuit will look like this. VOC value as 11.647 and both the resistors with 1.765 ohm. In order to find the maximum power, we can use any of the expressions for power, V into I or I square R or V square by R. I am taking the relation I square R and I have used another expression for I. By solving this, I got an expression as VOC squared by 4 RTH. Keep one thing in mind. Whenever you are trying to solve a question for finding maximum power, and that too using Thevenin's method, you need not have to derive all these steps for obtaining power. You can directly use the relation VOC square divided by 4 RTH. We can substitute the values 11.647 square divided by 4 into 1.765 and we'll get it as 19.22 watts. So this is our final answer, that is the maximum power that is obtained from this circuit. I'm sharing the complete picture of this problem. Just go through this and try to do this problem by yourself. Thank you for watching.